The Milky Way is moving through space at hundreds of kilometers per second, and it's not alone. When astronomers remove the universe's general expansion from the data, a leftover drift remains, pointing toward one broad direction. That direction became famous as the Great Attractor, an apparent gravitational something we can measure but can't easily see. If it sounds impossible, we investigate it. In a clean Hubble expansion, galaxies recede smoothly with distance. But real galaxies have peculiar velocities, extra motion caused by gravity from nearby structure. The local group, including the Milky Way, shows a consistent directional flow. The Great Attractor is basically the name we gave to the strongest-looking part of that flow. Redshift tells us a galaxy's velocity, but not whether that velocity is pure expansion or gravity-driven drift. So astronomers use independent distance tools, standard candles, scaling relations, and large catalogs. Once distance and speed are separated, the extra motion becomes a mappable signal. That's when the mystery stops being rumor and becomes data. With enough measurements, you can draw a flow map, not just where galaxies are, but where they're heading. Those maps show coherent streams along filaments, converging toward dense regions. The Great Attractor emerges as a gravitational low point in that terrain. It's not one dot, it's a basin in the cosmic landscape. Here's the catch. The Great Attractor sits near the Milky Way's plane, where dust and stars block our view. Astronomers call this the zone of avoidance because optical surveys see fewer background galaxies there. The sky looks empty, but the motion says it isn't. When sight conflicts with gravity, gravity usually wins. Infrared light cuts through dust better than visible light, revealing galaxies hiding behind our own. As infrared surveys improved, the blank zone started to populate with real structures. That doesn't reveal one monster object. It reveals a crowded neighborhood. The Great Attractor begins to look less like a myth and more like a heavily obscured region of mass. Massive clusters trap hot gas that shines in X-rays, making them detectable even when dust complicates optical views. X-ray observations act like a heat signature for hidden weight. They help confirm where dense clusters actually sit in that direction. The Great Attractor's pull starts to match real, visible structures, just not in ordinary light. One heavyweight candidate is the Norma Cluster, a massive nearby cluster located close to the zone of avoidance. It's large enough to bend local motions and fits the geography of the flow maps. For many researchers, it's a major piece of the Great Attractor puzzle, but the numbers hint it may be part of something even broader. In clusters, most mass is not in stars, it's dark matter. That means even if you identify every bright galaxy, you still haven't counted most of the gravity. The Great Attractor could be dominated by dark matter spread across a wide region. The unknown mass might be unknown only because it refuses to glow. Gravity leaves fingerprints. Gravitational lensing subtly distorts the shapes of distant galaxies. By measuring those distortions across wide fields, astronomers can infer where mass must be, even if it's dark. It's a way of mapping weight without needing light. In a mystery like this, gravity becomes the witness. The Great Attractor is often misunderstood as one thing. In reality, it's a convergence zone formed by clusters, filaments, and dark matter over densities. Think gravitational watershed, not cosmic monster. The name is dramatic, but the structure is distributed. When scientists mapped galaxy flows more comprehensively, they proposed a larger structure, Laniakea, the supercluster region defined by those motions. In that picture, the Great Attractor becomes a key basin inside a vast flow system. It's like realizing you weren't being chased. You were simply drifting inside a giant current. The mystery changes from what is it to how is the flow organized? Farther out, the Shapley supercluster is one of the most massive concentrations in the nearby universe. Even at great distance, its gravity can influence large-scale motion. Some models suggest part of the Great Attractor flow could be Shapley's pull in the background. The attractor might be a layered gravitational story. Cosmic motion is rarely a straight line because gravity comes from multiple sources. Nearby mass tugs strongly, distant mass tugs broadly. That creates curved flows and complex convergence zones. The Great Attractor is where those influences become most obvious in our local maps. Sometimes motion isn't only about attraction. Underdense voids can create an apparent push. If one side of space has less matter, gravity is weaker there, and galaxies drift away toward denser regions. A void near our region could amplify the flow toward the Great Attractor direction. In cosmic dynamics, absence can be as influential as presence. The Great Attractor is not a single black hole swallowing galaxies, and it's not proof of aliens or exotic physics by default. The scales and distances point to large-scale structure, clusters, dark matter, filaments, and voids. The mystery is observational. How to map what's hidden, not supernatural. The evidence keeps pulling us back to gravity. Every new survey reduces the blind spot. Better infrared catalogs reveal hidden galaxies. Radio observations see through dust. X-rays highlight hot cluster gas. As datasets grow, flow reconstructions sharpen. The Great Attractor becomes less of a shadow and more of a measured region. This matters because it tests our understanding of mass distribution in the nearby universe. It's a real-world check on dark matter models and the architecture of the cosmic web. It also reminds us the Milky Way is not stationary. It's part of a river of galaxies. Even our home is in motion. Here's the clearest takeaway. The Great Attractor is not one object. It's a gravitational basin carved by clusters, filaments, dark matter, and even nearby voids. We can't always see it directly, but we can see what it does to everything around us. The universe leaves evidence in motion. And if it sounds impossible, this is exactly where we start investigating.